After characterizing the user point process, now we come back to the distribution of R0 and Ri. So remember, R0 is the distance of selected active user from its tagged base station. So because users select the base station according to the distance, it means X0 is the closest base station from the UE0, which is at Y0. So what will be the distribution of this distance? It is same as we have computed before. The distance between X0 and UE0 is more than R. It means there is no base station in in the ball of radius R. So this will be given as probability that R0 it is greater than R is equal to e to the power minus lambda by f square. From this we can compute the distribution. So this is the exact distribution. Similarly, Ri, recall Ri is the distance of the ith user from its own tagged base station. And this user is also selecting the base station from the same law that it will select the closest base station. So distribution of Ri is also the same. This expression is also exact. Only thing we need to keep in mind that the RIs are not independent, they are correlated. And we have explained this reason before, because the users are selecting the base station from the same process, so the RIs will be correlated. This in generally means that RIs are not independent. It means if you want the joint distribution of R1, R2, R3, then that will not be equal to the product of the individual distributions. But again, you will see that if you try to compute a joint distribution of Ri, it will be very complicated and the analysis cannot be done. Remember, in the PGFL, whenever you use, we require the functions are only depend on xi. Similarly, if marks depends on the other base station points, then would be very hard to compute any performance. So what we do is we take Ri as a mark of each user I, and we assume this mark is independent, but we keep the distribution same as the distribution we have computed. So it means we are removing the conditioning between R1 and R2 and assuming that the base station 1 has mark R1, base station 2 has mark R2, which are independent copies of R1 R2. See, we are making an approximation, but the approximation may not affect the analysis. That depends on how much is the effect of these random variables. Since these RIs are due to different users, by changing little bit distribution of Ri may not affect the interference. What is crucial here is that this Ri does depend on the user location and the base station location also. And that may affect the interference a lot. We saw that because of the user location, of the typical user location and the base station location, there would be some reason in which other user interfering users cannot exist, and that is given that is represented by the active user density. So that would be more important because that area is close to the user and the tag base station, and if we do not model that correctly, the interference may be wrong. And because this interference is around near the user and the tag base station, this may have a crucial impact on the final value. The base station which are far away, basically the users which are far away, their interference is not a dominant one. So changing little bit their distribution by a little bit amount does not affect the overall answer. So this is just to say that we will remove the conditioning between R1, R2 and R2, R3, but we will keep the conditioning on all RIs conditioning of R0. It means once we know what is the value of R0, we will try to modify the values, the distribution of RI. So we will not remove conditioning of the serving base station and the typical user's location conditioning over RIs. What is the crucial impact would be is this, because we know RIs is less than DI. Right? This just means the serving base station of any user would be less than, that it will be nearer than the tag base station from this user, right? And the condition, and this condition comes because if it is not, then the tag base station would be its serving base station and then it will not be active. So once we know that given DI, we know RI cannot be more than DI. But if you look at the RI distribution, it can be anywhere between 0 to infinity. So we will include this condition in the distribution of RI. So this is just to say the distribution of Ri is 2 pi lambda Ri e to power minus lambda pi Ri square, and that is from 0 to infinity. But if I put the condition that Ri cannot be more than Di, so what we'll do is you look at the distribution of Ri goes 0 to infinity, and when we say that this is Di, which depends on the location of tag base station and the user I, and we say the Ri need to be less than Di. So we are going to truncate this random variable by Di. So how do we truncate a random variable? So this is a result. Consider a random variable x which has support 0 to infinity. Its PDF is fx and the CDF is capital Fx. The PDF of the truncate random variable x between a and b would be equal to, the PDF is given as original PDF divided by the CDF value at b minus CDF value of a, and then a indicator that x can only be between a and b. So this just means that first of all we are only keeping the density. So if you look at this and this indicator, it means if x is between a to b, we keep the density. If it is outside, then we make the density 0. And the denominator is just a normalization factor to make sure that final PDF remains a valid PDF and its integration would be 1. So this way we can also truncate Ri. So using the same formula, when we want to truncate between 0 to Di, so this is A and this is B, the distribution of Fri given Di would be equal to the original PDF, then the indicator that R is less than Di and more than 0. I have not explicitly write 0, and in the denominator also the CDF at the value Di, which is probability that R is less than Di. And we know the distribution of this R, original Ri, should be equal to original Ri, and that is equal to 1 minus exponential of minus lambda pi Di Ri square. That is coming from the PDF of Ri. So this whole thing would be a condition PDF, condition on Di. So you can see this actually means that I know the location of UE, which is at Yi, and I know the user typical tag base station location, and this distance is Di. So condition on this Di, I am conditioning the distribution of Ri. That just means that I am keeping the conditioning with respect to the tag base station. Okay, and if there is another user here, it may also have its own base station. Suppose this is R2. So I'll again do the same thing with this R2 also, but I am removing conditioning between R2 and this Ri just for the tractability. And you can see that as di increases, as the user moves away, then this truncation would not matter a lot because this limit of di increases. So you can compute, you can see that these are very equal as di goes to infinity. It means this effect is only morely important for the users which are close to the tagged base station. And you know that the users which are close to tagged base station are going to be the most dominant one. Now let us consider the ith pair which has UE at yi and the base station at xi. The distance between yi and xi is ri. So normally if you think U is located at yi and the tagged base station is at the origin, the interference caused by this yi at the tagged base station depends on the distance di. How is the distance between this yi and xi is important? This is because the transmit power actually depends on Ri. Why? Because uplink generally uses power control, which was not in the downlink. So what is a power control mechanism? It's an adaptive technique where all UEs associated to a base station change their transmit power such that the receive power at the associated base station from each UE is the same, regardless of their distance from the base station. So this means that when a base station see all the users, the base station kind of see all the users transmitting at a different power, but the receive power from each user at the base station is the same. It means the transmit power at each UE is going to be different. So let the required power level be P, then a UE which is at distance R from its associated base station will transmit at a power Pt such that the received power at the base station, which is Pt Cr to power minus alpha, is equal to P. This means transmit power is going to be equal to P by Cr minus alpha. Cr. This means that if R is more, then the transmit power will also be more. And if R is less, it means the serving base station is close to the UE, then the required transmit power will be less. Okay, so in this figure you can see the user 1 is close and the user 2 is far away. So user 2 will be transmitting at a higher power so that the received power at the base station from both of the users is same. And this is the case when the user is at the bad reception, it's far away from the base station, then user transmits at a larger power. And that is the reason you may have seen that in some cases the battery drains very fast. So there are different types of power control also. The one we discussed is called the full power control because you try to exactly match the received power at the base station. There is another variant which is called the partial power control with a factor epsilon. In that, what we do is we modify the receive power, we modify the transmit power by the following equation. You can observe a factor epsilon in the power. So P by C multiplied by R to power alpha into epsilon. So this epsilon was not there, or epsilon was 1. If you put epsilon equal to 1, then you get the previous expression. So epsilon is going to be between 0 and 1. Okay, so if I put it from the ith user where the distance between the serving base station and the U is Ri, then the transmit power will be of the ith UE will be equal to Pi is equal to P by C Ri to the power alpha to power epsilon. This I denotes that the transmit power is different from for each UE. So if you put epsilon equal to 0, you get Pi is equal to P. This means there is no power control and all the UEs have same transmit power. And if you put epsilon equal to 1, you denote the full power control. In that case, Pi is equal to P by C Ri to power alpha. This is same as the first equation. And if epsilon is between 0 to 1, you get different types of power control. So now let's talk about the SINR coverage. We are considering the tag base station and it is the receiver for the typical user. The interference at this base station will be caused by all the interfering UEs. So SNR will be given as S upon I plus noise. S is your serving power, I is your interference. Let's compute S first. So S is the receipt power, instantaneous receipt power from the user at Y0, and that is given by the transmit power of the UE, which is P0. Remember, 0 is the index for the typical UE. Then the path loss, which is given by C R0 to power minus alpha, and the fading H0. We can put the value of P0. We are taking a general epsilon power control. So P0 would be given by P by C into R0 to power alpha to a power epsilon and the rest of the terms, and you finally get P into R0 to power minus alpha 1 minus epsilon H0. Okay, you can see if epsilon is 1, you just get P into H0. So transmit power P, which we wanted, multiplied by a fading. And if epsilon is 0, then you get the same serving power without any power control. Now I can be computed same way. For this we have to compute the received interfering power from the ith user first. Okay, same way it will be given by the transmit power Pi of the ith user, the distance of this user from the tag base station, which is Di to power minus alpha multiplied by Hi. And there will be C also, but that will be cancelled in the same way as we saw in the past case, and the final answer would be P Ri to power alpha to power epsilon norm of Yi to minus alpha Hi. This is the path loss, this is the factor coming from the transmit power, and this is the fading. Therefore, the sum interference would be summation over all active users of P of this part. Okay, so this is your active user, and then what I can do is I can write in the original the potential user for point process summation if I include this condition that Ri is less than Yi. Okay, both are same. You can write in terms of the active user that you will use the density which was non-homogeneous, or remember this PPP, this was derived from the potential active UEs with this indicator condition. Whoever is satisfying this condition, we kept that UE. Whoever is not satisfying, we remove that UE. So both summation are different. So you can either take this and calculate the Laplace transform using a density computed for the active UEs, or you can use this, the second one, and use the density computed for the potentially active UEs. Okay, so this was lambda, and this was depends on the location, lambda 1 minus e to power minus lambda pi dl square, and di is nothing but norm of yi. So the assigner coverage probability will be computed in the same way as a downlink, but there would be some differences. One is because of the indicator, there will be the density is not homogeneous, and there are additional term RIs which are coming in the transmit power. These are random variables which you have to take care of. So assigner probability that assigner is above threshold is given by the serving power divided by the interference plus noise greater than tau. We proceed in the same way. H0 is greater than, and the rest of terms we move to the right hand side. And then now you will identify the random variables here are H0, I and R0. So first we condition on I and R0 and solve with respect to H0. So probability that H0 is greater than this variable, which is constant here once you condition on I and R0, is given by exponential 2 minus this whole term. This is coming because H0 is assumed to be a exponential random variable. Now we have to decondition with respect to I and R0. Right? So now we will apply this for this thing that same way, this Leibniz theorem, that since we are conditioning on R0, which is that there is a UE and there is a serving base station, for that the rest of the active UE, if you remove that UE, is still going to be a PPP. Right? If you assume the original active UE is the PVP, then if you condition on one UE and see the rest of the active UEs, that is still going to be PPP from Leibniz theorem. So this means this interference is caused by a unconditional PPP, or at least in the distribution they are saying. So now I'll first decondition this probability with respect to distribution of R0, which we have already computed. So here the only term which will be remaining is I. So now we have to, this term will have expectation respect to I. Right? Now we do the same thing. We break this summation into sigma square and the I term. This does not have I, so it will be taken out of the expectation, and the rest has an expectation with respect to I of the form exponential to the power minus some coefficient into I, and that is nothing but the Laplace transform form. So I can write the Laplace transform of interference calculated at the value 1 upon p tau r0 to power alpha into 1 minus epsilon, and this the noise term is also here, and this is the distribution of R0 for which we have to compute the expectation. Now we have to compute the Laplace transform of I. So I is given in the following form: the summation over yi from all active user process psi a, then the transmit power, and then the factor coming because of power control, then the path loss yi to power minus alpha, and the fading hi. So we have considered the active user process as a PPP with the density already calculated. So these locations are given in yi, and then we are assuming this Ri and Hi as the marks of this process for each point. So Ri is the distance between its serving base station to this user distance, and Hi is the fading from this to the tagged base station. We have already computed distribution of Ri and Hi, and we are assumed that they are independent. So the Laplace of interference can be computed in the same way. From the definition we know Laplace of is equal to exponential of minus si and its expectation. We just put it back and you get expectation of exponential minus summation term over a function of yi and mi. Mi is the mark. So we can apply the Laplace functional of the mark point process, and you will see it is the same as the PPP case. Only thing, there will be one expectation with respect to the mark. So it will be equal to exponential minus integration over the whole space, then the lambda density of the active user, which is non-homogeneous, so it depends on y. Then the function term 1 minus e to power minus function, and then its expectation with respect to the marks, which are hi and ri. So the density I will put, which is equal to lambda into 1 minus e to power lambda pi d square, and d here is norm of phi. Then this term would be equal to 1 minus e to power minus sp ri to power alpha epsilon into norm of phi to the power minus alpha into hi. So first we will try to calculate this expectation, and there are two random variables hi and ri, so we can try to compute expectation one by one. So first we'll compute expectation with respect to hi and then with ri. So inner term is exponential to power minus hi into some coefficient. So this can be computed using Laplace transform of the hi random variable, which is exponential. So we know if h is the Laplace exponential distributed random variable, the e to power minus ah, some coefficient to h is nothing but 1 upon 1 plus a. So we can here, and you will get this, and then you have to compute the expectation with respect to ri. So I'll do some further manipulation. Remember, 1 is also the expectation of 1. So I can write this in terms of expectation of 1 with respect to ri. Then I can take eri common from this term and this term to get this 1 minus this. Then I can do some manipulation and I get this just by taking the common denominator. And then I divide by this term in both numerator and denominator to get this. That is just trivial manipulation, which we also did in the downlink case. Now I will put the dense distribution, note the distribution of RA is given by this. So this was the original distribution, and then I truncate that u cannot be more than norm of y. So the expectation can be calculated by this term multiplied by distribution, and this indicator that u is less than norm of y, either I can put it as an indicator or I can put this is correspondingly just means that the limit of u will go from 0 to norm of y. Now you can notice this term will cancel from this term, and what you get is integration with respect to r0 r square r2 and condition an integration from u equal to 0 to norm of y, and then this term which is 2 pi lambda u e to power minus lambda pi u square divided by 1 plus s inverse p inverse u minus alpha epsilon norm of y to power alpha, and then integration with respect to u and y. So I can now try to further solve it. I can change y to a polar coordinate to become y dy, and then there will be an angle also, and this function does not depend on angle, so that angle integration will be just 2 pi. So now if we put this back in the original expression, remember the probability coverage expression we got was this, and this was the Laplace transform. If I put the Laplace transform back to this, I will get this expression. This is just, I'm just putting the Laplace transform value here. Okay, and Laplace transform we have to calculate at this coefficient, so I put, instead of s, I'll put this value. So some of the term will cancel, especially power, and this is the final expression. This is the expression we get. Now this is rather a complicated one, so I will take some special cases. Let's take a case which is noiseless scenario, means sigma n square is 0, and the full power control, that means epsilon is equal to 1. So if you take this coverage probability expression and if you put epsilon equal to 1, then you will see this term will become 0. This term will become 0 means this r0 to the power 0, so that is just 1. So you get Laplace transform of I at tau p inverse. There is no r0 there. Noise I have already putting 0, so this term, whole term will be 0. So this will be just integration of 2 pi lambda r e to power minus lambda pi r square, which is coming from here, and this Laplace term, and then dn. Now this does not depend on r0, so I can just take it out, and then it will become, so now let's compute the Laplace transform for epsilon equal to 1. We start from the original expression and just put epsilon equal to 1. This is the one you will get. Now to further solve it, what I do is I first notice that this is u minus alpha y alpha, so this can be written as y by u alpha. Now I notice the limit is from 0 to y. I put it back to the limit to 0 to infinity with an indicator that u is less than y. This is eventually the same thing. This indicator will make sure the integration only goes from 0 to y. But because of this, now the limits are both 0 to infinity. I will try to interchange the limits of u and y. So I put the dy inside and du outside, and the limits, because they are both same, they will remain the same, and the indicator u less than y and the same term. Now what I do is I do a substitution. I put y equal to ut. So in that case, you will see this indicator become t greater than 1. Wherever there was y by u, that become t. And then some substitution term will also come. Now after further manipulation, you will see that this indicator is t greater than 1, then this term no longer depends on t, so I can take it outside and this comes here. Now this part does not depend on t and this part does not depend on u, so I can separate them out. We know that if there is an integration fu du and ft dt, I can separate the integration to fu du multiplied by integration of ft dt. So if there is no single function which has both t and u, I can separate the integrations. So if you follow this, one integration with respect to t and one integration with respect to u, and then t has a limit from t, that t is greater than 1, so that limit will become 1 to infinity. Right. Then we can do some more substitution. I can put u square equal to z, and this u integration can be written to this. Now this is really simple. There is integration of z e to power minus lambda pi z dz. This can be solved very easily and it will become 1 upon lambda pi. So the whole integration, and this lambda pi cancels, so the whole I will become exponential to power minus integration from 1 to infinity, and this term. I will put this term back to the probability of coverage expression. So remember, the probability coverage expression was this, and this does not have r into it. So I will take this outside, and the rest will be just integration of 2 pi r lambda to lambda pi r square dr, which will become 1, because this is a valid PDF, and if you integrate it, should be equal to 1. So only term remaining probability Sn greater than tau is Laplace of interference calculated at tau into P inverse. I already know the value of Laplace transform of interference. I just put T P inverse in place of S, and once you do that, you get this expression. There will be further cancellation of P and P inverse, and what you get is exponential minus infinity to 1 2t 1 plus tau inverse t to power alpha dt. I'll do further substitution. What I do is I am going to make this as equal to u to power alpha by 2. The reason will be clear in just a minute. Once we do this, and this means tau to power minus 2 by alpha t square is actually equal to u, right? And what I did is I took the power 2 by alpha into both sides. Then if you differentiate this, this will be equal to this. I put this substitution back, and the same expression can be written in the following form. So u is this. So if you put t equal to 1, you get this limit, and if you put t equal to infinity, you get this limit. Rest is easy. Now this is in the same form in the downlink case. Remember, if we call this whole function as rho tau alpha, this will be nothing but exponential to power minus rho tau alpha. This rho tau alpha is the same thing which we got in the downlink case. So just to recall that in downlink case, we actually got that for the no noise case, the SIR coverage probability in the downlink was given by this. Similarly, in the uplink, we found for the full power control, the coverage probability is given by this. Both has this rho function which is given this way. But downlink is going as 1 upon 1 plus rho tau alpha, and this uplink is going as exponential to power minus rho tau. If we compare this, what we can find that exponential goes way faster. It means the SIR coverage of the uplink scenario will decrease faster with tau than the downlink comparator. And the reason is because the uplink case, because of the power control, you cannot get very high uplink SIR, because if you are at a very good condition, you will try to reduce your power. So because of that, when you increase tau, the coverage probability goes very fast. It means you cannot get more than that tau coverage probability with high probability.